Hello. Good morning. Actually, it's already good afternoon. It's early July. We are now all in Davis. We're continuing easy lectures on realistic modeling and simulation of earthquakes, soils, structures, and their interaction. Again, joining me as usual are Dr. Han Yang
Hello.
and Mr. Heshen Wang. Um,
Hi.
everybody is physically separated. Everybody's at home. I'm actually in my office because internet is really good here. At home, I get to share internet with others, and they're all overusing internet. So I get back here to the office. Today, this lecture is going to be about calibration of material parameters for interfaces, joints, and contacts. And again, as I mentioned before, our interface, our contact is a constitutive contact. We already have an interface between two materials, let's say foundation and soil, or foundation and concrete, or sorry, foundation and rock, or two concretes that, within a dam. So Mr. Heshen Wang is going to tell us a little bit about calibration of those parameters. So Heshen, please go ahead and start sharing your screen so we can get going.
Okay. Yeah, can you see this?
Yes, make it one
Okay.
slide, not continuous, but one slide at a time.
Okay, like this.
Perfect. Yes, make it a little
Okay.
bigger. Yes,
Yeah.
excellent, excellent.
Yeah. Yeah. Thanks, Professor, for introducing me. And yeah, today we're going to continue to talk about the calibration of the elastoplastic models for interface contacts or joints. And as I mentioned before, for common like a concrete to soil or steel to soil interface, we feel like it's a very good model to use the stress-based soft contact with nonlinear hardening shear behavior. So we will take this material contact constitutive behavior as an example to do the calibration. And this is a DSL, as you can see here in real easy. We have 9 parameters for this material model. The first 3 parameters is going to control the normal penalty stiffness behavior of the contact. And then we have initial shear stiffness, which give the initial tangential stiffness of the shear direction. And also we have 2 parameters for the normal and axial, for the normal and shear direction, the damping response. And also we have a parameter for the residual friction coefficient, which is essentially the tangent phi, where phi is your friction angle of your contact interface. And also it's very important to specify the shear zone thickness of your contactor. And as I mentioned before, the last parameter we have 2 choice. The user have 2 choice. User can either explicitly specify a normal of the contact plane, or they can use the automatic contact detection algorithm implemented real easy. And in that case, a user going to specify the surface vector relative tolerance to detect the different contact normal for the contact plane. Yeah.
So just a comment. So this damping that you mentioned, this is viscous damping. This is if you think about an interface where you have something that's going to open a gap and close the gap, there will be some suction, there will be some pumping of fluid, in this case air or water. And so this is the meaning of this in normal direction. And then in shear direction, it's really less than that. But this is again viscous dampers, these are essentially dashpots, do help stabilize simulations, and especially in this axial mode, which is very physical. It does help stabilize, and it's very physical for modeling. And then the other thing, the contact shear zone thickness, usual experimental data shows that for granular materials, it's anywhere between 10, 15, 20, 25 particles. So in this case, and you'll show some numbers, it's going to be a few centimeters at most. But it's also very useful to know that contact shear zone thickness, because that is also used to calculate the actual energy, specific energy, something that Han talked about in some previous lectures. So yes, please go ahead.
Yeah, so we're going to first start with the 3 parameters for the normal axial behavior, which is the parameter for initial axial stiffness, essentially, and also the stiffening rate, and also the maximum axial stiffness. So the initial axial stiffness is the initial slope of the, when you look at this normal stress and also the penetration plot, is the initial slope. And the stiffening rate is to specify how much you want your axial penalty stiffness to increase. And also we usually have a cap number, the maximum axial stiffness that you cannot, your your stiffness cannot exceed this number just for numerically to avoid some numerical issue. Because if you have a very large stiffness in your system, the metric is going to be yield conditioned. Yeah. And here I'm showing you the different behavior for different numbers of the initial stiffness and the stiffening rate. And we generally put maximum axial stiffness to be 20 gigapascal. And you can, and it depends on your different behavior, depending on your contact interface, you can choose a proper number of the initial stiffness and the stiffening rate. So the key point here is that on one hand, you do not want to be your contact to be too soft, because otherwise you will have a too much unrealistic penetration. But on the other hand, you do not want your count to be too hard. You do not want to have very large penalty stiffness, because that will create some numerical issues, and also it's not too realistic. Say if you have a steel or concrete on the soil. Yes, Professor.
So just
Yes.
to note, so this is really one stiff material, concrete or steel, on relatively soft material, either rock, softer rock, or soil. In this case, what you have is a number of particles, and you have something very stiff on top. And so this is the reason why this stiffness is not immediately going up, why the forces are not going, they're essentially exponential. This was observed experimentally. First time, I think, by a number of people, but one of the first models came from Ignacio Carol and Paul Gens from Barcelona 20 plus years ago, almost 30 years ago, where if you think about it, this is very stiff part, and you have a contact with one particle, second particle, third, and so on. So the actual increase is exponential.
Yeah,
on the other hand, if you have a contact with two very stiff, let's say polished metal or polished material and another polished material, this is where the hard contact plays a role. But in our case, most of the time it's actually soft contact. Yes, go ahead.
Yeah, that's true. Yeah. So for the modeling of earthquake soil structure interaction, like as Professor mentioned, that we usually choose the soft contact for the concrete to soil or steel to soil interface. And here we have choose relatively a medium, like soft contact behavior. We will choose the initial stiffness to be 400 megapascal and the stiffening rate to be 1000. And as I mentioned before, we're going to put a cap on the penalty stiffness to be 20 gigapascal. And in addition to the axial normal direction, more importantly, you also need to calibrate your shear direction behavior of your contact. And depends on whether you have any experimental data or what data you have. For example, here, if you have a very good test for the smooth sand and the steel interface as done by Sahura and Razari in 1997, and you can calibrate your parameters to match the experimental behavior of your shear direction. As you can see here, the residual coefficient is around the 0.5. So you can just put the 0.5 as the residual friction coefficient as the plateau of this value. And also, you can calibrate your initial shear stiffness to match the stress strain response. As you can see here, we have been choosing the 3 megapascal to fit really well with the experimental data. But yes.
And so just to say, so this is for different types of materials. So this case, smooth steel versus sand, but I think you'll show a table that has different combinations of materials. Yes.
Yeah, but in case if you do not have any a very good this stress strain experimental data, we have some recommended default residual friction coefficient for you to use. As you can see here, you can go to our lecture notes section 511.9, and also you can reference to this. I think this is an Army Corps manual.
Navy manual for construction in places where you let's call it foreign places.
Yeah, they have done a lot of experiment on different contact, different types of the contact. The concrete or steel to different types of soil, or concrete to concrete. Yeah, they will have some recommended values for you to use as the frictional coefficient. For example, here I'm showing you the coefficient, frictional coefficient for the mass concrete against the different types of soil. As you can see here, if you put a mass concrete on the clean sound rock, then you might want to use 0.7 as a friction coefficient. But while if you have a mass concrete on the very stiff clay, you probably want to use a 0.4 or 0.5 as the friction coefficient. Yeah. So Yes, Professor.
So essentially mass concrete, meaning that you're pouring concrete directly onto material. There's another type of friction that's in that manual, and that's also in lecture notes, is the formed concrete, which means much smoother concrete, and then you put some material inside. And there's also steel, rough steel and rusty steel and smooth steel and so on.
Yes.
But one of the main things is that if you use this type of data that was developed without, I mean, doing some tests, but some different material, not the material that you have, it's a good idea to do a sensitivity study and to see, you essentially go through these numbers and you try to use lower bound numbers, medium numbers, and upper bound numbers and see the actual response. If
Yes.
these frictional coefficients, if this frictional behavior does make a response in a significant way, that means that those coefficients, those parameters are important. Then you actually might want to do tests. If they don't change the actual behavior that much, then you can just use these recommended coefficients.
Yeah, that's true. Yeah. Yeah, as the professor mentioned, that is always to considering some uncertainties that when you input to the real ED simulator. Yeah.
Yes.
And we also have some the other parameters which generally you might not have a good experimental data to calibrate, and I will suggest some values for these other parameters. For example, the axial and the shear direction damping, as Professor mentioned, that there are some physical reason that why we use some damping, because of this suction of the air or some suction of the fluid, and generally we would put if the put some like several like 15 to like 200 par per second for this axial damping and shear damping. And also there's another parameter which is specify the thickness of the shear zone. As the professor already mentioned that this parameter is really depends on like your interface condition, depends on the grain size or depends on the roughness of the contact interface. And generally we would put 5 millimeters to like 1 to 2 centimeters for these parameters, just like this range. And the third parameter, which is really important, which is the contact normal vector. If you want to explicitly specify the normal of your contact, and please remember that you should always specify the normal vector to be from the first contact node to the second contact node. If you flip this normal vector, the contact will behave like a hoop. That will introduce a totally different physical behavior and also might some convergence issue for your contact. Yeah.
Just a note. So if you flip and there's a big note in lecture notes and there's a big note in DSL, if you flip nodes 1 and 2, you're really modeling, and maybe you want to do that, you're really modeling Velcro. So instead of contact like this, you're really modeling a pull out, which has some tension. So you can actually model Velcro as well, if you want. But you need to know this. As an engineer, as an analyst, you need to know that you can do that and that you want to do that. Yeah, go ahead.
Yeah. On the other hand, if you have a pure like a solid interface, you might also want to use this automatic contact detection algorithm in real easy. And in that case, you also need to specify the surface vector relative tolerance. And from our experience, we recommend you to use a 1E minus 4 at the tolerance to distinguish different contact normal. Yes, and with that, I think you can have all these parameters set up for your contact contact element, and you can look up this reference for more information. And this is the menu that we already mentioned that from the Naval Facilities Engineering command. And also you can also refer to lecture notes for more parameters information. And also again, we want to give thanks to our collaborators and also funding resources. And also you can check out our website for more information on videos and tutorials. Yes.
Thank you very much.
Thanks.
So I'll stop recording. I'll just note again that all these videos and these slides are going to be uploaded to the website, and I'll do this a little later today. Thank you very much. I'll stop recording.